System Dependability Co-Analysis via ConcertoFLA. We demonstrate two functionalities. The first functionality is the automatic generation of fault tree, using System Dependability Analysis via ConcertoFLA. The second functionality is automatic generation of multi-concern fault tree, using System Dependability Co-Analysis via ConcertoFLA. We follow a four-step process. In the first step, the architectural specifications of a system are defined using ChessML. In the second step, failure behavior of the components is modeled. In the third step, ConcertoFLA is performed to calculate the failure propagation paths. In the final step, these failure propagation paths are transformed to generate a fault tree. In the end, if the system is not dependable enough and needs refactoring, all steps are performed again until the certain level of dependability is achieved. To define the system, first we create a chess project. We navigate to the New Project Creation Wizard dialog and select the chess project. In the next step, we create a class diagram in the component view to define the interfaces, components and their implementations. In this class diagram, the elements are defined using the palette on the right side. Elements are dragged and dropped in the editor. All of the defined elements can be visualized in the Model Explorer view. For example, the interfaces, realizations, components and their implementations. Once all of these components are defined, the next step is to assemble them into a system. We demonstrate the functionality using Attitude Control System. In this design, the system is composed of 6 components. The system takes sun sensor measurements and angular rates on its input port and produces the control torque on its output port. Each of the composing components receives values on its input ports and produces the output on its output ports. After defining the system, failure behavior is modeled for each composing component. We apply FLA behavior stereotype to all the components. And, then specify the failure behavior using Failure Propagation Transform Calculus, FBTC, rules. Each rule represents a mapping of faults received on the input ports to the output ports of the components. For example, in this rule value course failure on SunVec input port is propagated to ConSunVec output port. Using FBTC rules, 4 types of behavior could be specified for component. 1. Component propagates the failure. 2. Component transforms the failure into different type of failure. 3. Component sinks the failure. And 4. Component is the source of failure. In this demo, the modeled failure behavior for all components is propagator. We perform ConcertoFLA by selecting the ConcertoFLA analysis menu entry. The analysis generates the failure propagation paths and store them in a file. In the final step, we generate the fault tree by selecting the Generate Fault Tree menu entry. This opens a file chooser dialog. We navigate through the files to select the file, generated in previous step. This generates a fault tree with the top event referring to the value course failure at control torque output port of the system. The fault tree presents the causing events of the top event including the root causes or basic events. This flowchart shows the steps for the second functionality. There are 2 additional steps in comparison to the previous functionality. The first additional step is specializing failure behavior for security concern. The second additional step is the trade-off analysis between the different attributes to improve the design. Next, we demonstrate the additional step, that is specialization for security concern, and then generate a multi-concern fault tree. To specialize the failure behavior for security concern, error model behavior stereotype is applied to the component of interest. Next, a state machine diagram is created and error model stereotype is applied to the state machine. The error states and transitions between them are modeled to define the component behavior in the presence of a security attack. A data spoofing attack transition which is related to the unauthorized modification of service threat could lead to an error state. The attack exploits the missing data integrity schemes and cause a failure having value course failure on the ConcertoFLA output port. After this specialization, the ConcertoFLA is conducted to generate the multi-concern failure propagation paths file. The multi-concern fault tree is generated in the same fashion by selecting the FD generator menu entry. The file chooser dialog is navigated to select the file for generating the multi-concern fault tree. The generated fault tree contains the unauthorized modification of service security threat, which is due to the data spoofing attack on the input port of the component and the missing data integrity schemes vulnerability of the component.